So in this video, we are going to talk about energy. We're going to introduce the concept of temperature, as well as how to convert from different temperatures. So the first thing we need to learn about energy is the law of conservation of energy. And I like to think of it more as just the law of conservation. This part, the of energy bit, can be interchanged because we are going to learn a law of conservation of charge, a law of conservation of energy, a law of conservation of matter, and things like that. And so they all basically say the same thing, except whatever is being conserved, we just swap that word out. So for the law of conservation of energy, we say energy can never be created or destroyed under normal conditions. It only changes form. If we were talking about matter, then just substitute the word matter. If we were talking about charge, then swap out charge. So these are the laws of conservation. And what they mean is that you can't destroy or create the things that we're trying to conserve from nowhere. In other words, you can't just make energy appear out of thin air. It has to come from somewhere, and you can't make energy disappear. It has to go somewhere. All right. So there are different types of energy, and the way energy moves, it usually moves from these different types. So we have thermal energy, which is the motion of atoms. We'll come back later to that, which is basically heat. So thermal energy, think heat energy, think atom motion, and the way we measure heat is through temperature. There's chemical energies, the energy stored in chemical bonds. This is definitely the least obvious of them. For example, nobody thought that if you mix charcoal and some salts and stuff together, you would get black powder, which can be used to make bombs. And so chemical energy tends to be a little bit less obvious if you don't know what's going on. Light energy, okay, anyone who's gotten a sunburn can attest to the energy in light. A lot of times light energy and heat energy usually get, eventually when you get to physics and things like that, we'll lump them into the same category, but for right now we can call them separate things. It doesn't really matter. And nuclear energy, the energy coming from inside an atom, we will come back to that later on and spend a whole unit of that. So there are two forms of energy that we worry about. We worry about potential energy, that's energy stored in chemical bonds, and we worry about kinetic energy, or we think about kinetic energy, that's motion energy, or how fast the molecules are moving, which is, again, our thermal energy. All right, so those are our two forms. Basically, kinetic and potential, the only things that you've heard of forever. The only thing I'm changing in chemistry, we're going to call them chemical potential energy. So in physics, you worry about potential energy like, oh, if there's a, piano suspended from a string, there's your classic example, and you don't want to walk under it because if it falls, you get squished. Chemical potential energy is different. It's like you've got this, unknown powder, and if you put a spark to it or you shock it, it could blow up like a bomb. And so it's a little bit different. It's still potential, meaning it could do this if you ignite it and you start a chemical reaction, but it's more specific to chemistry. Measurement of energy. So we measure energy through temperature. Temperature is not energy. Temperature isn't even heat. All temperature really is a measurement of heat that science decided was the number we were going to use to represent heat. It's just like, for example, why did we choose to make, 1 degree the size and volume that it is? Someone decided it somewhere. All right, so I'll get more into temperature on the next page and we'll explain it in greater detail. But temperature is the average kinetic energy. I will abbreviate it as the AKE pretty much all year. And what that means is real simple. It is the average kinetic energy. Let's break it down. Average means, obviously, we know average. Kinetic energy is the energy of motion. So it's the average motion, or you could think of it as the average speed. So I like to think of temperature as like the average speed on the expressway. So if you have an expressway and let's say the average speed is 65 miles an hour, that does not mean that all cars are going 65. Some might be doing 100, some might be doing 65, some might be parked off to the side of the road because they got a flat tire and they're doing 0. But the average speed is the temperature, and that's how I like to explain it. So not all particles have the same kinetic energy. We just explained that. But they are, for the most part, always moving. Now, can molecules stop moving? Yes, they can. I will explain that in a second. But for the most part, they're always moving. All right. And if we go a step further, we can say, all right, if we've got lots of movement, then we have a high average kinetic energy, which means high temperature. And if we have very little movement, then that means we have low average kinetic energy, low temperature. All right, so that's pretty much it. So if the molecules are really moving very fast, we would call that hot. And if they're moving really slow on average, then we call that cold. We have two forms of temperature that we are going to talk about. There are others, but there's two temperature scales. We have the Celsius scale, which is based on water. So the reason scientists did this is pretty simple. They said these are two temperatures that the average person comes into contact with all the time. Anyone who lives in a cold climate knows what the temperature of freezing water is, or how cold something is when it freezes. And anyone who's ever cooked anything ever knows the temperature of boiling water. So these were very common temperatures in the average everyday life. And so the Celsius scale was made by a scientist, and so he basically created a thermometer and he put it in boiling water, and the line on the thermometer went up, and he marked it, and he called that 100. And then he put it in ice, and he marked that, and he called it 0. And then he took a ruler out, divided the increments up, and he said, all right, got 100 increments, and poof, Celsius scale. That's why we say temperature is just a measurement of heat, because it's a number that we came up with that just represents how hot or cold something is. There could be different scales, just like the Kelvin scale. So Kelvin came along and said he was going to base his scale on this concept of absolute zero. And so Kelvin knew that since temperature was just a measure of molecular motion, that if you slow molecules down by making them cold, eventually, if you keep going, they will get so cold and they will move so slow that they will eventually stop. He called that absolute zero because if you think about our car analogy, a car cannot move any slower than 0 miles per hour. It cannot move any slower than stops, because even if it's going in reverse, that's still a speed. Like, that's hence the absolute term. I mean, I think the absolute term works on two levels. You could say absolute zero. In other words, you can't get slower or colder than that. Like, you absolutely can't get any colder. And it could also be like a mathematical reference, like the absolute value and things like that. You really can't have a negative speed. It's not like if I get hit by a car that's going in reverse, I somehow don't get hurt because the car's going backwards. So that's the general idea. So this is absolute zero is the temperature at which all molecular motion has stopped. So I'll write that down. So all molecular motion has stopped. You cannot get colder than that because molecules can't move slower than not moving at all. He then, the nice thing that he did, and it's convenient for us, is he made his, the size of a Kelvin the same size as a Celsius unit. Okay, so think of it like that. So therefore, if the temperature went up by 10 C, and the temperature goes up by 10 K, that's the same amount of temperature increase. Now, as long as the numbers aren't the same, because 0 C and 0 K are two very different temperatures. But, for example, if the temperature went from negative 273 C to negative 263 C, or it went from 0 K to 10 K, that would be the same temperature change. Okay, just the numbers are slightly different. Now, there is a formula that we use for converting Kelvin to Celsius. It's something that you do have to know. You don't have to memorize it, but it is, because it is in the back of your reference table. I'll put it up here at the top. K equals C plus 273. And so here's some example problems. I'm going to do one or two with you, and then that's it. So let's do 300. We'll do negative 55C. Everyone will think that's the hardest. So K equals C plus 273. So I always like to write my formula out, plug in the number you don't, that you know, negative 55. You can plug in K or plug in X. You solve for it and you get 218 Kelvin. So these two temperatures, negative 55C and 218 Kelvin, are the same temperature. Okay, and I always like to do it this way, and on your practice problems, I'm going to have you write them out like this and do it this way and show me the math every single time. And then let's do 275K. So now I take my 275, plug it in for the Kelvin, solve for C by subtracting from both sides, and I'll end up with 2C. So 275K is 2C. They're the same temperature. So that's how to do these problems. Remember to write them out and solve them. As you get better at this, I'm still going to want you to write these out. The number one mistake students make with this formula, it is very easy, obviously. You're either going to add 273 or subtract 273, but when you don't write it out and you are new at this, you will make the mistake much more easily of adding when you're supposed to subtract, or vice versa. And that's where the number one mistake on these problems is trying to do it in your head, rushing, and then adding or when you're supposed to subtract or reverse. Last thing we're going to talk about is heat flow. So heat always flows from hot to cold. Always, no exceptions. And here's the reason why. Think of molecules. If the molecules are hot, then they're moving around really fast and they are banging in and bumping into everything, okay? If the molecules are cold, then they're moving very slowly. I don't know about you, but I don't know of a single person on Earth who's ever been hit by a parked car, okay? Because if the molecules aren't moving, then they can't bang into anything and they can't that's how they transfer their energy. So the ones that move really fast will collide very often and with high speeds to molecules that are not moving very fast. Another example is, for example, I have a pot, I put it on the stove, it gets really hot, I touch the pot. Who gets burned, me or the pot? Clearly I get burned. Why? Because the pot is really hot and I'm really cold, and the energy is going to transfer from the pot to me. It doesn't work the reverse. All right. So that concludes these notes. If you have any questions, I'll be in class